Hi, everybody. My name is Bhargav Shivkumar, and I'm going to be talking today about how we use gradual types in a language used to specify derivative contracts at Bloomberg. So let me start off by talking about what a derivative contract is. So a derivative contract is a type of a financial contract, and very informally speaking, a financial contract is an agreement that two parties participating in a financial market enter. And a derivative contract is a type of financial contract that derives its value from an underlying asset or a group of assets. When I say an underlying asset, what I mean is something like an equity, an interest rate, foreign exchange, and so on. Now, there are many types of derivative contracts, and a forward contract is an example of such a derivative contract. What a forward contract is that it's a commitment to exchange an underlying asset for a fixed price and on a future date. So, for example, you want to buy euro and you want to pay for it in US dollar at some point in the future, and you want to protect yourself from any market fluctuations in the forex value. You'd enter into a forward contract wherein you can do this transaction. You can exchange your USD for euro at a fixed price at a particular date in the future. Now, another type of a derivative contract is a swap, wherein you make a commitment to do multiple such exchanges of the underlying asset over a period of time. There are many more types of derivative contracts like options, Himalayans, Phoenix Notes, and so on. But for the purpose of this talk, it would suffice to understand what a forward and a swap is. So at Bloomberg, we have this Bloomberg Contract language, BCL for short, to describe such contracts. And to give you a very brief introduction to BCL, BCL is a statically typed language with Hindley-Milner style type inference, and it supports an extensive feature set and an extensive type system. And it was inspired by a paper by Simon Peyton-Jones and others, which talks about a programmatic way of expressing contracts and composing such contracts as well. So this example over here describes a forward contract which exchanges underlying forex, and it starts out by declaring some components of the contracts, like the date on which the contract is to be executed, the amount, the currencies being exchanged, and so on. So when you're writing such a contract, you would typically use some combinators or primitives to help you write such contracts, like the date function, which converts a string to a date type, or the current FX rate primitive, which converts, retrieves the current forex value at that particular point in time. And the whole point of this piece of code is to define a contract, and it's these two lines here which do exactly just that. So you have the receive and give primitive, which are used to create contracts which perform the whole operation of exchanging your forexes. Both these contracts need to be acquired on the date, which is specified by the variable t, and your AND combinator ensures that both these contracts are acquired. So this is typically how end users or users of BCL would utilize BCL to write contracts and specify them programmatically. Now, while designing BCL, we were in a little bit of a design tug-of-war, and we were thinking about whether we should go with static typing or should we go with dynamic typing. And typically in such situations, language designers tend to pick a typing paradigm either based on users of that language or applications that is going to be built with that language or various other criteria. We too had a little bit of a back and forth what we should use, and we recognized that static typing is definitely beneficial for us because of the correctness being an important criteria in contracts. And what I mean by that is it is important for us to catch errors earlier on in the contract definition process than later on. But on the other hand, this is a commercial language, and we would want to make sure that we cater to a larger user base. So we would want to make the language as flexible as possible so that many more people can adopt this language. So we were left with this question as to, given such varying interests, who do we appease? So to put this dilemma into a little more context, let me talk a little bit about the types of users who use BCL. So we have one type of user who we call as end users, who are typically finance professionals, and they have some sort of experience in dynamic languages like MATLAB and Python and so on. And our end users are concerned with development speed. So all they want to do is they want to be able to code contracts quickly, and then they can analyze the contract behavior. And for this particular reason, they like the flexibility that's offered by dynamic languages. So definitely dynamic typing helps them achieve this goal. A point I would like to note over here is this whole notion of flexibility is very subjective. So some users may feel that any amount of static type checking is inflexible. On the other hand, we have maintainers. Maintainers are software engineers with extensive experience in statically typed languages like OCaml, C++, and so on. Their main job is to implement language extensions, standard library functions, and they're also tasked with the responsibility to maintain backwards compatibility as BCL evolves. And so their primary concern is ensuring correctness of any standard library functions they provide, or ensuring that when the language evolves, it doesn't introduce any new errors. Static typing alleviates their pain by catching any bugs much before, and they don't percolate down to the end user. So we're back to this question as to how do we give both these types of users what they need. And if we were to put a little thought into it, what we ideally need in this situation is a statically typed language that feels roughly dynamic. One way to achieve that is to provide type inference. Now, type inference is a very nice way for you to avoid explicitly annotating your program with its types, and it gives the user a feel of a very dynamically typed language. But the fact remains that under the hood, everything is still statically type checked. So you are going to possibly end up with static type errors. And as I mentioned earlier, that you're going to have users who are going to feel any amount of static checking is not being flexible enough. So we would want to provide our users with a way in which they can actually defer this whole type checking process to runtime. And this is where we feel gradual typing definitely fits the bill. So gradual typing has ideally been used in such situations where you want to provide a middle ground for users who want to experiment with both static as well as dynamic typing. But what it provides for us is that we can now have coexisting static and dynamic code. And also, static code is not going to be blamed for any runtime type errors. So this provides a really nice bifurcation in which our end users and maintainers can code in BCL and be comfortable with how they write their code. So, of course, gradual type seems to fit the bill to solve the problem that we have. But how do we go about incorporating this into BCL? And in order to answer that question, I think a good way to work that out is to look to how other people have done it for inspiration. So we identified three main components for introducing gradual types into a language. So first, you're going to need the ability to annotate your terms so that you can differentiate between what is inferred and what is explicitly dynamic. Second, you're going to need to add this dynamic type to your list of existing types. And third, you're going to need an algorithm to unify your dynamic types with other types and type variables. So if you notice, I'm talking about unification of types and type variables because I'm approaching this incorporation of gradual types from the perspective of a statically typed language with type inference. So this gives me actually a nice way to broadly classify the different approaches that languages utilize when they want to, embark on such an endeavor. So there seems to be a static first approach where you start off with a statically typed base language and you add more and more dynamic type checking. And on the other hand, you have a dynamic first approach where you start off with a dynamic base language and you add more and more static type checking. Examples of languages that were developed with a dynamic first approach is you have languages like TypeScript, TypeTracket, Hack, variants of Python, Clojure, etc. And on the other hand, with the static first approach, it's an observation that there seem to be lesser mainstream static languages that introduce this notion of gradual types as defined by Seek and Taha. Of course, they have some support for dynamic types. For example, C# and Java introduce a dynamic type and they have a way to perform some sort of runtime inspection on it using reflection, very similar to what Abadi and others have proposed. And on the other hand, you have languages like SML, OCaml, and Haskell, which again don't support gradual types, but do support some form of dynamic typing, either through GADTs or type classes and so on. But all of these are not as seamless as how gradual types would be for our situation. There is also a small section of work out there which addresses this whole issue of gradual type inference. So they start off with a static based language, and they look at how you can add dynamic types into this whole type inference process. And those two works are two important works in this bucket. Basically, would be one by Seek and Vajrajani and the other by Garcia and Simony, which addresses the same problem, albeit from slightly different approaches. So what we want for BCL is an approach that fits into BCL. What we want to be able to do is we want to be able to infer static types and explicitly annotate dynamic types. So what I mean by that is, let's say I have this increment function as defined over here, and I annotate the increment function with the type dynamic to int. What I want to be able to do is I want to statically infer the type of, let's say, x in the body of increment, or even the return type of the increment function. And I want to be able to dynamically check the argument that is passed to the increment function. So if you see this, at some point, this kind of involves exploring how this dynamic type is going to unify or interact with all these various types that's being inferred. So, as I mentioned earlier, BCL has a Hindley-Milner style type inference, and we use Hewitt's unification algorithm. And now we're trying to incorporate the gradually typed lambda calculus. And whenever you have to incorporate gradual types into your language, you have to deal with this notion of consistency, or the relation consistency between types. But unfortunately for us, consistency really doesn't describe how dynamic types would be related to type variables, because type variables are an aspect of a language that performs some sort of type inference. But Seek and Vajrajani have already studied a similar approach, and they come up with this consistent equal relation, which deals with how dynamic types can play well with type variables. Now, we can't use this approach wholesale, but we can definitely draw inspiration from it. So we can try to introduce this notion of consistent equal relation into our own type inference algorithm. And of course, it follows that we would have to expand this out to make sure that this relation can support more complex types, like recursive types or structural composite types and so on. So in this way, we were able to incorporate gradual types into BCL, and we go into depths of our implementation in the paper. But all this is going to be a moot point if we are not able to bridge the gap between our end users and maintainers. So let's see, with the help of examples, if gradual type really lets us achieve our main goals. So we wanted to provide our end users with flexibility by introducing gradual types. And let's see if that's possible with this example. So we saw the forward contract defined earlier on. This is the same forward contract, just I've just made that out into a function. I've named it fx forward, and now this function takes the date, currencies being exchanged, the amount, and so on as arguments to that function. This little piece of code over here is the swap contract, which I, again, initially explained what it does. And a swap contract, to recollect, is basically a contract that does multiple exchanges over a period of time. And if you were to think about this programmatically, it literally translates to mapping this forward over a series of, or a list of dates, because all the swap is a series of forwards. Now, at this point, I'd like to mention that this is a very nice way in which you can compose contracts. So you can use smaller contracts to build much more bigger and complicated contracts, which is an advantage of expressing contracts programmatically in a language like BCL. So our end users typically would perform such a task, and they would build much more complicated contracts by using many smaller contracts as subcontracts. So if our end user were to go ahead and execute this in BCL, they're going to be hit with a type error, and this is going to be a static type error. The error is going to say, hey, fx forward expects a date, but it got a string instead. And this is a very valid error, because if you were to see, the fx forward function expects a date type, but at the point in which fx forward is called, it is mapped over a list of strings. So the ideal way in which our end user needs to address this would be to use something like the date primitive we saw to convert this list of strings into a list of dates. But it can so happen that our end user at this particular point of time only wants to input this contract into our system to study the way in which various subcontracts behave or interact with each other. And at this point of time, the exact dates on which the contracts are going to be executed might be irrelevant for them. So they would want a way in which they can, bypass this static type system to be able to analyze the contract behavior. And this is exactly what gradual types gives them. So with gradual types, I could annotate this list of strings as a list of dynamic types, and the static type system is not going to complain anymore about this type mismatch that occurs. And the end user can go ahead and try to analyze the behavior of various parts of the contract. Now, if the end user doesn't address this issue in the future, they are of course going to encounter a runtime type error when they execute the contract. But at least now they're aware of existence of such a thing, and it's up to the end user to address it at the appropriate point of time. So clearly, gradual type provides an escape hatch for end users who feel very constrained by the static type system. All right, so what about our maintainers? Do they get anything? So our maintainers are really happy with being able to use static typing and ensuring that whatever code they write is ensured to be free of any type errors. But they can also use gradual type to enhance our end user experience and give them some tools to better express contracts or better better write code whatever they're writing. So there is a nice use of contracts as templates in Bloomberg. So what happens is templates are written by end users who have a particular expertise in derivative contracts. They could be somebody who has a better understanding of the markets or a better understanding of how to write such contracts. So these templates are basically functions that produce contracts, and they're stored in a database. And any other end user who wants to use these templates can do so through a UI and can instantiate these contracts by providing arguments through that UI. Now, it would definitely be beneficial if these templates can be used in BCL code. And this is exactly what the maintainers can provide through a load template primitive. So the load template primitive can be used to load these templates which are stored in the database into your contract code. So for example, if my forward contract was a template, I can load that template into my code and then use it in a swap contract, just as I did previously. But this follows that the load template needs to return a dynamic type, because your templates could return various types, and you want to use the same primitive to load any kind of template. So not just the subcontracts, you can also use these loaded templates for, maybe performing some sort of a minor change in the code. So like, for example, if you want to load the forward contract and, put some limits on it or cancel it when it hits some conditions, this sort of primitive helps make any such additions or evolutions to your code. So of course, we now maintainers have a way in which they can enhance the end user experience, and our end users also have something to take away, because now they have a new way in which they can utilize the templates that are present in our system. Now, we have kind of achieved our main goal of providing this common ground for our end users and maintainers to use BCL, but gradual type seems to be a gift that keeps on giving. So we get a lot of add-on benefits by adding gradual types, which was not our original intention for adding gradual types, but it's still something that we can use. An example for such a thing is that we can now do some sort of ad hoc polymorphism. So let's say I want to define a contract wherein I receive an amount in dollars equal to the noon temperature in NYC. And I can go about doing that using the scale combinator. So what the scale combinator would do is it would take this time varying value, which is the noon temperature in New York City, and it would multiply all the payments in the contract by this time varying value. So if you were to think about this very intuitively, this seems like it can be very much more simplistically handled by the multiplication operator. So this is exactly what we can do with the gradual types help. We can make sure that we can use the multiplication operator for this for defining this contract, and then the multiplication operator would resolve it to the appropriate combinator when the types are resolved at runtime. Now, of course, it follows that we now would need a way to inspect types at runtime, and more than a disadvantage, this sort of a function would be a very good advantage, and it would help us provide some more features that can help enhance how users write code. For example, if we have a runtime inspection ability, we can write some Python-esque type conversion functions. For example, an any to string function, which would take any argument, convert it to string, or an any to date function, which would take an argument of any type and convert it to a date. So apart from these, sort of advantages, there is an added advantage that we get, which is not just as a result of adding dynamic types, but also as a result of doing it so in a static first approach. So in compilers, often they can do some sort of optimizations with the help of static type information. Now, in a dynamic language with gradual types, any unannotated types are implicitly dynamic. And for a user of such a language to leverage these static optimizations, they would then need to go ahead and annotate their entire program. But with BCL, unannotated types are implicitly static. So our users don't miss out on these optimizations, and they don't have to go through the effort of having to annotate their entire program. So we can say that gradual types definitely makes not just life easier for our users, it definitely gives us a lot more value-added benefits to make sure BCL is a much more extensive language. So I would like to conclude this talk by talking about where we want to go with this whole work. So it is our general observation that dynamic typing seems to be preferred by a lot of users, especially those with a without a computer science background. And on the other hand, static typing is very essential in ensuring correctness in domains where correctness is important. Gradual typing gives a very good middle ground, and it's something that literature should explore to make sure that we can identify various innovative uses of it. So to further this cause, we intend to gather feedback on how our users and maintainers use gradual types. And we believe that we would be able to get new and novel ways in which we can apply gradual types to the whole domain of financial contracts. And we would like to come up with a more detailed paper armed with such a data as to how gradual types are being modified and used by our users, and even come up with various other applications of gradual types in our domain as well. So thank you all for your time, and please let me know if you have any questions.